My name is Julie Onton. I have a PhD in neuroscience, and today I'm going to talk about the HPN technology and how it's affecting the brain. To do that, I'm going to do a little bit of basic neuroscience and a little bit of basic electrical engineering, and finally talk about the technology and how it's stimulating the brain. And I will talk a little bit about some related technologies and how they work in the clinic. So the neuron is composed of a cell body, like other cells in the body. What's unique to neurons is it has appendages called dendrites, and those come out of the cell body area. And then it has one axon that leaves the cell body, and that goes to other neurons, and that's how it communicates with them. At the end of this axon, there are synaptic terminals, and that's where neurotransmitter is released, and it communicates with the postsynaptic cells. And postsynaptic cells sense these neurotransmitters through receptors, and then it responds to that and might send a signal onto the next cell. So these neurons use the axon to communicate to the next cell through electrical current. And when the current comes to the end of the axon, neurotransmitter is released, and that's how the cell communicates to the next cell. And neurons accomplish this by maintaining a negative ion potential inside their cell. So the inside of a neuron is negative relative to the extracellular space. And it does this by separating charged ions. The ones that we care most about, that I'm going to talk about, are potassium and sodium. So potassium is very concentrated inside the cell and not as concentrated outside the cell, and sodium is the opposite. There's a lot more sodium outside the cell than inside the cell. And then crucially, inside the cell, there's a lot of charged proteins, which makes the cell more negative than the outside. So along the cell membrane, there are ion channels. The ones I'm going to talk about are for sodium and potassium. The sodium channel is generally closed because there's a big ionic gradient that will cause sodium to rush in if they're open. Potassium is a little bit different, and that's because there's two forces on potassium. One is a diffusion force that goes outside of the neuron, so it wants to go out because there's not as much potassium outside the cell. But there's an electrical force keeping it inside, and that's because the cell is negative and the positive potassium is attracted to the negative cell. Synapses are propagated down the axon by triggering sodium channels to open and causing the depolarization. And as one part of the axon is depolarized, the part right next to it becomes depolarized as well, and it's sort of a chain reaction. Following that, the potassium channels rectify that depolarization by opening and causing the membrane potential to become, again, negative inside. And you can just imagine this as a moving front going down the axon, causing electrical potential changes along the membrane. And so when it gets to the end, the beginning of the axon is at normal resting potential again. And you can imagine you have all these ions going back and forth, which are creating this depolarized state that neurons like. How do they get back in? So how that happens is there is a sodium and potassium pump that puts the ions back where they should be. So sodium on the outside and potassium on the inside. So the bottom line about all of this that I want to communicate is that so neurons are highly interconnected. They're always talking to each other, and this happens through electrical currents. So along each axon and at each synapse, there's a delicate balance of electrical charge and current. And so when you disrupt this balance, this is going to result in altered neuronal communication. And so this is important when we're thinking about HPN, and all of this very specific ionic current moving around is likely to be changed. I'm going to talk about some numbers related to HPN and the related technologies, comparing the strength of the signal and the strength of the stimulation for each of them. I'm going to add in here ECT, or electroconvulsive therapy. This is a simulation that's similar to TDCS and TACS in that it's applying a current across the head. The only difference is that the strength is much, much stronger, and it's used pretty exclusively for intractable depression. But as you'll see, if you can improve with a lower power therapy like HPN, it would probably be beneficial. So ECT causes an induced current density, or amps per meter squared, of 225. In contrast, TMS, which I mentioned is much stronger than HPN, is 3 amps per meter squared. TDCS, which is still stronger than HPN, is an order of magnitude smaller, 0.3 to 0.8, and HPN is 0.0056 amps per meter squared. In terms of applied amps or milliamps, ECT is 800 milliamps. TDCS is 1 milliamp, and for comparison, a AA battery is 0.3 milliamps, and HPM is only 0.02 milliamps. In addition, because HPN is only on for brief bursts, it amounts to only about 0.03 seconds per session, and I'll explain why that is in slides following this. But in contrast, TDCS is on continuously for, as I said, about 10 to 20 minutes. So there's a huge difference in amount of current that's being applied. Another way to look at it is the electric field that's induced in the brain, and that's in volts per meter. So TACS, this is related technology to HPN, very closely related technology, induces an electric field of 0.4. And finally, peak power of HPN produces about 2 microwatts, and a AA battery is about 450 microwatts, so much, much less than your common AA battery. So the HPN stimulation consists of a very specific waveform and pattern. It's basically consists of bursts of a complex mix of megahertz frequencies, and this is just an icon for it, but basically it's an alternating current that's very, very fast, much faster than brain speed frequencies, and it's meant to just be a burst, just a very quick stimulus, and it's only on for a microsecond. The way that it stimulates the brain at brain speed is that it does a certain number of these per second. So imagine we're looking at 1 second of time from 0 to 1, and you have a series of bursts, 1 through 11 bursts. And what that constitutes for the brain is an 11 hertz stimulation, which is right in there at brain speed. 10 hertz is about an average speed of brain oscillations. And this causes the brain to feel an 11 hertz stimulation. So the HPN protocol, and there's a couple that you can choose from, but this is the basic protocol for what it's doing when you press the start button. It first detects EEG power, and it'll do that for 1 second, and it'll see for that first second what the peak frequency is. So here, this is a 10 hertz peak. And then it will determine the feedback frequency, and that's based on what you set to be the offset or what protocol you choose. So let's say it starts at 1 hertz offset. That means 10 plus 1 is an 11 hertz stimulation, like I showed in the last slide. In the next second, from 1 to 2 seconds, it does another power transform and finds the peak frequency there. Here it's still 10 hertz, so then you go to the offset frequency, which has now gone up 1 to 2 hertz. So you have 10 plus 2 equals 12 hertz. So for that second, it's going to stimulate at 12 times per second. And then again, in the next second, it's going to do another Fourier transform and find the dominant frequency. Here it's a different frequency. This is now about 7 hertz, but my offset is 3. So 7 plus 3 is 10 hertz. So you can see every second is a different hertz feedback, and it's based on what the current power is in the brain and the offset. And this continuously changing feedback is desired. That's the point. It's not trying to entrain the brain, it's actually trying to disentrain the brain. The key to HPN appears to be the stimulation pattern and waveform that is responsible for its clinical success. And it's probably just a benefit that it's actually lower power than TDCS that should be a safer application. The size of the current that's applied in HPN is incredibly small, and it seems like a stimulation that's a microsecond isn't going to affect the brain very much. But we do know that the brain is adaptable, that it gets used to things very easily and very quickly. So the idea that you would switch up the frequency of the stimulation makes sense, and it makes sense from the point of view that the brain is constantly trying to adapt to it, but it never can. So in that sense, it's disrupting the activity in the exact way that we're trying to disrupt activity. that the stimulation itself is so small, even though it's patterned at brain speed, the stimulation being so brief, I think it blows our human minds that would matter. But even if it's brief, all of those ions that I was talking about do feel that shift, even if brief, and that's disrupting the activity that was there before. I don't know why HPN is necessarily more powerful, but from clinical reports, it appears that it is. And so it seems an advantage that we're able to stimulate the brain in a very powerful way with not a lot of current flow, which makes the whole technology safer in my mind.